Brayton cycle. What cycle do gas turbines work on? This is a cross-section through a gas turbine. There are three main components in it. The first is the compressor, where air which is taken in is compressed. The second part is a combustion chamber, where fuel is added and ignited. The third is a turbine, where work is done which drives the compressor. We can represent a gas turbine, therefore, by these three components. The first is the compressor, second is the combustor, and the third is the turbine. We will treat each one of these as a separate control volume. A gas turbine is assumed to work on an idealized Brayton cycle. This consists of four processes. The first is a compressor, in which we have isentropic compression. Next, the heat input is assumed to be at constant pressure. The work output is done in a turbine where we have isentropic expansion. And finally, the heat rejection is assumed to be at constant pressure. We can show a Brayton cycle on both PV and TS axes. The first step is isentropic compression. Next is constant pressure heat addition. Then is the isentropic expansion. And the final stage is the constant pressure heat rejection. We can calculate the amount of heat transfer during the Brayton cycle. The heat addition is at constant pressure, so QH, the heat added per unit mass of fluid, is equal to H3 minus H2. And we can write that as Cp T3 minus T2. The heat rejection is also at constant pressure, so QC, the heat rejected per unit mass of fluid, is equal to H4 minus H1, which equals Cp T4 minus T1. We can now calculate the thermal efficiency of a Brayton cycle. The thermal efficiency is defined as the net work output divided by the heat input. This is QH minus QC divided by QH, or 1 minus QC divided by QH. The efficiency, therefore, is equal to 1 minus T4 minus T1 divided by T3 minus T2. We can write this in terms of temperature ratios. We now need to evaluate what these temperature ratios are. In a Brayton cycle, processes 1 to 2 and 3 to 4 are both isentropic. We can therefore write that T2 upon T1 is equal to P2 upon P1 to the power gamma minus 1 divided by gamma. However, P3 is equal to P2 and P4 is equal to P1. So we can therefore write P3 upon P4 to the power gamma minus 1 upon gamma. But since 3 to 4 is also an isentropic process, this equals T3 upon T4. So therefore, we can write that T4 upon T1 is equal to T3 upon T2. If we now look again at the expression we had derived for the thermal efficiency of a Brayton cycle, we can cancel out the terms in T4 upon T1 and T3 upon T2. The efficiency of a Brayton cycle is 1 minus T1 upon T2. Since the process 1 to 2 is isentropic, we can replace that temperature ratio by a pressure ratio. So the efficiency is 1 minus P1 upon P2 to the power gamma minus 1 by gamma. We define the pressure ratio, R sub P, and this is defined as being equal to P2 upon P1. This is the ratio of the pressure at the exit of the compressor to that at the inlet of the compressor. The efficiency of the Brayton cycle then is 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. The larger the value of the pressure ratio, the greater the efficiency. We can calculate the work required by the compressor. The work per unit mass of fluid equals H2 minus H1, and this equals Cp, T2 minus T1. The work done by the turbine, W2, is equal to H3 minus H4, and this equals Cp, T3 minus T4. The back work ratio, which is the ratio of the work required by the compressor to the work done by the turbine, equals H2 minus H1 divided by H3 minus H4. We can improve the efficiency of a Brayton cycle by using a process known as regeneration. The gases which are leaving the turbine are hot and they still have a significant amount of energy in them. Instead of exhausting these to the atmosphere directly, we take the exhaust gases and pass them through a heat exchanger known as a regenerator. As they go through the regenerator, they exchange heat with the air which is about to enter the combustor, and they raise its temperature. The temperature of the air leaving the regenerator is at state 5. The heat which is now added in the combustor equals H3 minus H5. This is less than it would have been without the regenerator, because then the amount of heat added would be H3 minus H2. We therefore reduce the amount of heat which is added and increase the efficiency of the Brayton cycle. The performance of a regenerator can be described by its effectiveness. This is defined as the enthalpy increase in the regenerator, defined by the maximum enthalpy increase possible. The highest temperature that can be reached in the regenerator is T4, which is the temperature of the exhaust gases leaving the turbine. We therefore define the effectiveness as being H5 minus H2 divided by H4 minus H2. This, if we assume constant specific heat, equals T5 minus T2 divided by T4 minus T2. We can increase the amount of work that we get out of a Brayton cycle by using a process known as reheat. In this, we expand the hot gases in 2 stages rather than a single stage. When the gas comes out of the first turbine, we expand it only partially, from 3 to 4. The gases then go into a second combustor known as the reheat combustor, and we heat them back up again to stage 5. It then expands through a second turbine. The total amount of work that we have got from the combined 2 turbines is H3 minus H4 plus H5 minus H6. The advantage of using reheat rather than a single turbine is that to get this much work, we would have had to raise the temperature very high. Now we have managed to increase the amount of work that we get without increasing the maximum temperature that the turbines see. We can reduce the amount of work required to compress air by using intercooling. In this, the compression is done in 2 stages. First, the air is compressed from 1 to 2. Then it goes into a heat exchanger known as an intercooler, where it loses heat to the surroundings and the temperature is reduced to T3. It is then compressed again to the final combustor pressure. By cooling it in between, we reduce the amount of work which is required for compression. To summarize, gas turbines operate on a Brayton cycle. The Brayton cycle thermal efficiency increases with the pressure ratio. The pressure ratio is limited by the peak temperature the turbine can withstand. Regeneration recovers some of the energy in the turbine exhaust and improves efficiency. Reheat increases the work output by using a 2-stage turbine. Intercooling reduces the work done in the compressor by cooling the air as it is being compressed.